So today we are going to discuss, you see the title of the lecture is Building a Finite Element Model. So you may argue, well, we are talking about that since the beginning, you're right, but we've been talking about that mainly on the theoretical, from the theoretical point of view, in order to formulate the finite element equations, element equations, global equations, combining them and solving the system. We saw how some solution strategies and so on. Now today the idea is just to see how we practically implement all the things that we saw together into a finite element model. Imagine that we have a software available. You will have available one software next Thursday, but there are many available on the market. The one we're going to work with is not the only one. It's not the best one. It's just a simple one that we can use together to play a little bit. Okay, it's used also in practice. It may happen that when you go to work in the field, you will need to use the same software. However, it's just one of the possible software. Okay, just keep this in mind. We're not doing this class to learn how to use that specific software. We want to learn the methodological aspects to be able to use any software, theoretically. Okay, that's our idea. So we'll go through what we call 7 steps to build a finite element model. Instead of the 6 steps that we had to formulate, here we have 7 steps, we added one. And then we will see an example. I will see if we can do everything today, otherwise we will continue on next Thursday, right? Okay, so we start with the 7 steps to build a finite element model. Do you know where this picture is taken from? It's a nice staircase, isn't it? It's from Sri Lanka, if I remember well. Right, so it's a staircase that goes up to a temple. Now, the 7 steps. You will find some analogy with the 6, obviously, with the 6 steps we followed to formulate the finite element method. Luckily, there are some things in common. So step number 1 is the discretization. So the first thing we have to do is to discretize our finite element model. You see there that we say that today, many commercial softwares will assist you in this process. It means that you will have some tools available to build your finite element mesh. It depends on the software. The one we're going to use will build the mesh automatically. Will allow you some control on the way he builds the mesh. However, it will do it in an automatic way. So we can use automatic generators with many softwares. The second step is that of building our boundary condition. So after that, we have discretized, we have set the region, we discretize the region, then we set the boundary condition as we know, and then we have to assign the material properties to each finite element in the model. All finite elements will need to have their specific material properties, which also mean a constitutive load, elastic, plastic, hardening, softening, whatever we want. Step number 4 is that requires the assessment of what we call the initial stress state. The initial stress state. Why do we do that? Well, we do that because, as we said several times, for a geotechnical problem, very often, we do not start from zero. We're not starting the world. We always do something in a world that existed already for many years. So we have an initial stress state. When we go there to put our building and we need to design the foundation, there is an initial stress state in the ground. If we excavate a tunnel in a rock mass, there is an initial stress state in the rock mass. So that's why we need to implement and assign to our numerical model the initial conditions. Good morning. Good morning. Right? So the initial stress state is something we need to assess. As you can read here, this can be computed by applying gravity. So we live on Earth, we know that we have gravity, 9.81, and that's the kind of force we want to apply to determine the initial stress state. So sometimes we can assign the initial stress state if we know it perfectly, or we can compute it by assigning gravity to the model. So we have these two options, but we'll go through it. Next step, number 5, is that requires to define the stages of our computation. So not only we have to assign all the rest, but we have to set how many stages we want to compute. Because if we are building a foundation or excavating a tunnel or preparing a diaphragm wall, there will be some construction stages that you use, that you need to complete your construction. And so we want to reproduce the same kind of construction stages in the model as well. And once we've done all this, we are ready to compute. And when we say compute, it means we want to solve the system of equations. When we were talking about the theoretical formulation, we were saying now we need the solution strategies, we find a solution, we compute the displacement, and as secondary quantities, we compute stresses and strain. That means compute, and luckily, this is, with a commercial software, this is done automatically by the software. But as I mentioned already, we can control the tolerance, the number of iterations, and so on, so that we can check the quality of the solution. We can control the quality of the solution. And the very last step, and this is definitely new with respect to what we said earlier, we need to interpret the results. So it's not just that we compute and we get the results and we say, that's it. But we need to check if the results are appropriate, if the kind of prediction we are making to the numerical model corresponds to the performance we are monitoring. And all this is called interpretation. This is a very important part of the numerical modeling procedure. And of course, remember, try to keep this in mind. We will never finish our flowchart with the computation. We will always need to interpret the result. And that is, let me say, the added value that a human civil engineer can bring to the process. Otherwise, most is done from the computer. Okay, but interpretation is definitely human. So let's go through all these 7 steps together, and maybe I can. We have a number of slides here, so we can follow them. But let me use the blackboard also, and let's consider. Let's take the problem of a deep tunnel. Okay, that's our problem. So we have the ground surface up here. This tunnel is going to be built by, let's say, we're going to have a primary lining. I need to do it bigger so that you can see it properly. So just to define our construction stages, okay? We're going to excavate this tunnel. We're going to excavate the upper part first, then the lower part later. But before we excavate the lower part, we install what we call the primary lining. So this is going to be the primary lining, maybe light blue. Right? So this, let's call it primary lining. Then later on, we are going to install final lining, which is made like this. Let's do it in one single step. Maybe in a real construction, this is going to be done in more than one step, because maybe we're going to do the inverse arch first, and the string line and the crown later. And just to simplify, let's say that this is the final lining. Right? So we have a ground surface up here. Let's consider that this is a deep tunnel. How do we define a deep tunnel with respect to a shallow tunnel? Those that went through the tunneling course or rock mechanics, that you've seen this. How do you define a deep tunnel with respect to a shallow tunnel? The numbers of diameter we have here. That's right. Okay, if they are more than 2, we say it's a deep tunnel. Normally we say like that. Okay, so let's say that the cover here is bigger than 2 times the diameter. So let's say that the diameter is around, I don't know, it could be a highway tunnel, the equivalent diameter, because this is not a circle, clearly. Let's say that this dimension is something like 14 meters, okay? And here we have a depth of, with respect to the tunnel axis, let's say that this is 300 meters. Right? So that's the geometry. This is the problem. We want to design a tunnel at 300 meter depth with this geometry. Construction sequence will require us to excavate the first part, install the primary lining, excavate the second part, install the final lining. Okay, that's the sequence. It's a bit simplified with respect to a real problem, but just to make it on the blackboard, right? Good. So we want to study this problem with, we want to build a finite element model of this kind of problem. So the first thing we have to do is to define the geometry. On the slide, you see the geometry. Here, you see the geometry of a circular tunnel close to the surface. This is a problem of a shallow tunnel. Okay, different problem from the one we're doing here. So how can we define the geometry here? So any suggestions? Please participate from the classroom and from home. You can type it on the chat where we can read it. So what is the first thing we have to do? What do we need to discretize in terms of boundaries of the model, for example? How do we set the boundaries of the model? Sorry, I did. Okay, so last time we probably said a good rule is saying this is 40 meters. Since this is a deep tunnel, we can consider a model distributed in any direction or at least 10 times the equivalent diameter. 140 meters on this side, 140 meters on this side, 140 meters and 140 meters, right? Okay, so let's do that. So let me put my channel here. And let me build the model. So this dimension, but this dimension, this dimension, this dimension, they are all 10 times this equivalent diameter, right? So let me put it here. Bigger than 10 times the equivalent diameter. And look, 10 times the equivalent diameter means 140 meters. Okay? So it's somewhere in between the ground surface and the tunnel. But let me tell you one thing. If this was just 100, not 300, but 100, okay, then it would imply that 140 would go above it. Does this make sense? No, why not? We don't? You don't need it. There's no ground above that. This is what you want to say. Any other comment? This is correct, but it's not what we're going to do. Any other comment? From home? You cannot set appropriate boundary conditions. Well, look, if we consider a tunnel deep. When we said in rock mechanics 2 diameters, what was the hypothesis then in terms of the state of stress? Do you remember that? No, it's not with respect to K0, but it was almost right. We have a uniform state of stress, but not in terms of, not a uniform state of stress, sorry. We have a constant state of stress with respect to depth. So the state of stress is not changing with respect to depth. Why? When we have a shallow tunnel, we usually say that gravity has an influence, and so we consider that the state of stress will change with depth. So for a shallow tunnel, we would do something like this. This is a tunnel close to the surface, okay? We will consider that the state of stress increases with depth, and this is gamma times h, right? And z, sorry, let's put it z, which is better. And when we have a deep tunnel, this is deep, so I'm not going to put the contours, we say that the state of stress is constant. And then we will apply something like this. Constant with depth. And we usually say, okay, gamma times z, but z is the z at this point, and we keep it constant all over. In fact, when we use Kirsch solution or Carranza-Torres Ribacchi solutions, this is what we're doing. We are considering that the state of stress is constant all over. Okay, so that's the difference between shallow and deep tunnel. Now let's go back here. I said, well, let's assume that this is 100, and so we have 140. We go above that. Well, this is not an issue. If we are assuming a deep tunnel, it means we have to go like this. We don't care how big the model is, because the hypothesis is that the state of stress is constant. So it's not an issue that we go above that, because it's just our model of reality, our representation of reality. We assume that the state of stress is constant, so we need the boundaries to be far away, far enough, not to influence what happens here, but then it's not an issue. They go beyond the real boundary. Whereas, all what I said is wrong if we are in a situation like this. Because in that case, we have to do as she said, we have to stop the boundary here, and then we have an issue of boundary conditions. So we have to say, well, what kind of boundary conditions do we put here? Well, in case of a ground surface, it's going to be a free surface. In case of a deep tunnel, we will need to set boundary conditions. Okay? So the model is a schematic representation of reality. Always keep this in mind. So we may do strange things like going beyond the ground surface if we do it properly. Okay? So let's go back up here. Luckily, in our case, this is 300, so we did not have to argue on that. And we can build our model like this. We need to discretize. Discretize, which means dividing all the region in smaller elements. So let me do it here just to... and so on. Okay, I'm not gonna do it everywhere. So we have to discretize, as we said last time, and I'm not going into it because we said this already. We need denser mesh in the area where we have more stress gradients. We know that already. Okay, so this is going to be a mesh we like because we have big elements down here, not as big as I made here, but maybe like this. We have denser mesh in this area. And that's it. And you can see the mesh on the slide. You have a denser mesh in this area. which is the area where we expect more stress gradients. Right. The next step is that of defining the boundary conditions. And also here we already said a few things earlier, because we said, okay, we can assume rollers, we can apply forces, stresses. So in a situation like this, and since this is a deep tunnel, I'll input rollers everywhere, which means that I will have a hinge here. So this is not the ground surface. So as he said, we have to be careful with the boundary conditions. Okay, and then we have rollers, 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 and rollers. Okay? Boundary condition is applied at the nodes. That's why I'm drawing them like this. They are applied at the nodes. Okay? And we know we can have rollers, hinges, so that we fix some displacements, or we can apply forces and surface loads and things like that. However, we remember that when we apply, for example, like this, a distributed load, like we have here in this slide, then in our equations, in the computation, we're not going to put a distributed load. What are we going to put? Instead of, can we apply distributed load in our finite element equations? We have to apply to the nodes. So that is not going to be a stress, but it's going to be a force. So from these distributed load, we have to compute the forces at these nodes here. So we like to draw it like that because we understand it like that. We are engineers. We like to see the distributed load is applied there, distributed good. But then in the computation process, that distributed load will become point forces applied to the nodes. So we will need to compute this. The software is going to do it 99% of the time. But in general, we need to compute those forces and apply them to the nodes. So we have to consider, well, we saw this already. It depends on the shape function. We use that to compute the nodal forces. And this is how it occurs. So for example, a distributed load like this, strange distributed load on this triangular element will be considered in the equations like a force applied here and another force applied to this node. Whereas a point force as this one is going to be considered a point force. When may we have a point force? Well, look, for example, this was a shallow tunnel. Let's say that here we have, continue on, then we have a diaphragm wall, okay, and then we have an anchor. You know what an anchor is? In tirante, okay? An anchor, we usually say, okay, the anchor, we apply a load, I don't know, let's call it T, that's a point force. If we have our model here with finite elements, then at this node, we're going to apply a point force, exactly, inside of the distributed one. But whatever we do, we have to compute these ones. So here you have a sketch of different possible distributions. The usual ones we have, constant or triangular, which is this and this. These are the ones we use 90% of the time, okay, in geotechnical engineering. We may have things a little bit different, but 90% of the time, we will have a constant distributed load or a triangular shape of the stress. And in this case, you can see this is L, and there you have your force. And this is easy because you simply divide it by 2, okay, if you consider the L and then the thickness of the stress. If it's a triangular force, then you have 1/3 and 2/3. And what about this? Well, this is the distributed load, which is applied to a finite element, which in fact has one node here, one node there, and what is called a mid-side node. We did not talk about this yet, well, we may know that elements exist where we also, instead of having only these three, we may have what they call mid-sized nodes, some additional nodes with the same finite element. This is a special finite element. The software we're going to use will allow you to apply these kind of elements. What is the advantage of this? Well, that you have more nodes. So you have more points where you are computing the displacement. Not only 1, 2, and 3, but 6 in one single triangular element. So it's a way to have a more, like having a denser mesh. Here you have more nodes in the same computation. So in that case, this is how you would distribute the forces, and again, for a triangular distribution. Okay, it's just for you to have it there as a reference. Material properties. So let's assume that here we have an homogeneous graph. No, let's assume it's not homogeneous. It's 2 layers. That's maybe easy. That's maybe better. So we have it's a horizontal layer, for example. This is geotechnical unit number 1 up here, and then we have geotechnical unit 2 down here. Okay, 2 separate geotechnical units. That means 2 separate set of properties, maybe 2 different constitutive laws. Could be that one is we can consider it elastic, another one elastoplastic, or this may have a softening behavior, this one may have a hardening behavior. We don't need to use the same constitutive law. One of the big advantages of using numerical methods is that we can consider the appropriate constitutive law for each separate material. So if we do that, it means that we have to, once we have determined the properties for both of them, which means we have run laboratory tests, we have interpreted laboratory tests, we have a geotechnical report available that we can read and understand, and we have a proper set of properties. So exactly what you are doing in your group project. You had some tests, you had to interpret them, you had some in situ tests, and final task is building a table with the parameters. Table for GU1, a table for GU2 that lists GU1, and you have a list of your parameters: Young's modulus, Poisson ratio, collision, friction angle, and all what we need. Once we have that, then we can come here and assign the properties to the elements. So we will say, for example, if GU1 is from here, let's say that this one is going to be GU1. And this is going to be GU2. Now, here we have some problems with line geometry. It's not a very well done mesh in this case, because I decided later to have 280 units. But if I would do this properly, I would try to set some straight line here so that remember we said the nodes are aligned. We want the nodes to be aligned. I haven't done that here, so what can I do now? Well, I can say, okay, this is going to be violet, this is going to be violet, maybe this one is going to be violet, and I'm going to use green, which means GU2, these ones. So in fact, in my model, it's not going to be a straight line, but it's going to be something like this, my contact, which is not exactly reality. However, we are far away from the tunnel, so it's probably not going to affect that much our computation. It may be acceptable, but of course, this is something that we need to check. In the picture here, you have 2 examples of fairly complicated geology. In this case, this is an underground cavern, which with different with complicated geology, if you see, and each color corresponds to a geotechnical unit. So each color of that picture has been given different properties, and you see that the mesh is following properly the geology. And the same with this picture here, where we have a tunnel close to the surface, and you see that the geology shows an inclination of the soil layers, and this is a situation you can find in the field, and also the mesh is following this kind of geometry, and in that case we put nodes along those green lines that separate the different units. So, and then you assign properties, different properties, the yellow and the green, they will have different constitutive load, different properties, and that's it. So any query up to here? Any query? Yes, please.
The software will be directly, or I have to define the boundaries?
You have to define it.
I have to define it.
Yes. You have to define it, and it's defined when you discretize. When you discretize, you need to know already what is your problem. So you say there is a boundary there. I need to consider it when I build the mesh. So the good way was to put nodes along this line. So to have a straight line here, change the geometry of the mesh in this spot, that would be the best option. What I did here is, how can I say, a compromise, because it's easier to build the mesh as I did, and it's a compromise because I have this, which is not exactly what happens in situ, but it's far away from the tunnel, so it may be acceptable. Okay? But it's something you have to do when you discretize. For example, this picture here, this was made by using the software you're going to use, and you will see Thursday that in order to do exactly what you are asking, you need to build these green lines. They are, in that specific software, they are called material boundaries. So you need to build a material boundary, which means, let me put a material boundary here so that then I can apply to different properties. But that's how that specific software works. Others will do it in a different way. Okay? Any other query from home? Are you fine up to here? Okay. We haven't seen much new. These are things we discussed it already, but we just put it in the good order. Now we are entering a bit of new stuff. So step number 4 among the 7 steps we had earlier was assess the initial stress state. So this is what we want to do now. And as we anticipated, there are 2 possible ways to introduce the gravitational stress in a model. One way is that of performing a stress analysis where all the elements in the mesh are subjected to gravity loading with appropriate boundary conditions and unit weight. The second way is that of assessing the initial stress state in the model as we compute directly. So what does this mean? Example. Here. Do we know the state of stress in this model? In this problem, sorry. Do we know it? We can know. We can do. Sorry, I didn't get it. Say it again.
We can make it and we did not.
And how did we do it? Okay, you can make it situ test. That is, but from what we have here, do we know state of stress? Look, consider that I should add one line. Can you estimate? They don't see me if I stay here. Can you estimate the state of stress in this model? We are engineers. Let me tell you that K naught is equal to 1. This is something you didn't know, but let me tell you K naught is equal to 1. But You could answer anyhow.
So we multiply gamma.
So this is 300, and we have Gu1 here and Gu2 there. So we probably have two different gammas, and we don't know that, but this we can say this is I don't know, this was 140. So let's say this is 200 meters. Okay. So in our model we have both of them. So we can make 200 times gamma 1 plus 100 times gamma 2, and we get the vertical stress. Exactly. So we know the stress state. We know it. And if we know K naught, and if we don't, we can make some assumptions, we also know the horizontal stress. So we perfectly know, or at least we may estimate, based on these computations, the vertical stress and the horizontal stress for our application. We can estimate that. Of course, we can make some in situ tests in order to check if this is appropriate, if our estimation is correct, this is good. We can make an estimation, then we can check it in the field, but we can estimate. So that means that we could assess, we can implement into the model an initial state of stress by using method number 2, by simply saying, look, your state of stress is this one. So you assign to each element sigma V and sigma H as you have estimated. You directly assign it, okay, as it's written there. You set the initial stress in the model as you computed it. So you assign it as an input data. That's one way. And it's a convenient way in a situation like this, where we are considering a deep tunnel and everything is constant. That's convenient because everything is constant. We just make a very simple computation as you did, and you write two lines, you assign it, it's done. It would be a little bit more complicated if we have gravity, or if we have maybe, if we have, I don't know, the ground surface is not like this, it's going to do something like that. The geology is more complicated. Then what is the initial state of stress? Well, we need to compute it up there, then down here it's going to be different. That's not that easy. So in that case, we can use step number 1, method number 1, which means running a numerical analysis to compute the initial state of stress. So what do we do? Well, we make a model without any construction, the initial condition. We assign the material properties, the unit weight to each element. We apply gravity to the model. So we say, oh, look, you are on Earth, you need to use G. And we compute. What's going to happen? This is going to settle. This element is going to put its weight on the second one, this on the other one, and so on. The elements that we have on the bottom, they will carry all the load of the other ones on top, exactly as happens in situ. And the software is going to compute the initial state of stress at each element in the model. So that's method number 1. Running, if you want, one stage of the computation. This is already one stage of the computation, which is just needed to determine the initial state of stress. We haven't done nothing yet. It's just to start. Before we start, we already run a stage of our numerical model to assess the initial state of stress. Okay? So we have these two methods. This is easier because we simply compute it and assign it. The other one takes a little bit more time because we need to compute it. We need to run one stage of the numerical model. Look at this. This is an example of a shallow tunnel close to the surface. Boundary conditions are set like this. We assigned the unit weight to each element. We applied gravity in this direction. We have to say the direction of gravity because it's a numerical model. We could apply gravity in this direction. The other one, we can do whatever we want. So we have to assign gravity in the vertical direction, and this is the result. With the color scale, you see dark color is 0 and the white color is a higher value. So after the computation, the stress is increasing with depth, which is exactly what we wanted to get, because in this case, we want a triangular distribution of the stress. Now, when we do this, by using method number 1, consider that model over there, you will have, look, this is that model over there, okay? So we are assigning unit weight to each element, then we are setting gravity. So this is going like this. It's going to settle a little bit, because this put its weight on the other one, on the other one, on the other, and so on. Because initially everything is 0. But once I give a weight and the gravity, it will settle. The one on the bottom has some boundaries, so it's not going to change, but the one on the top will go down. And what we will see is that we will have a displacement at this node, going down, a displacement at this node, and so on. This one is going to be fixed. So we have this will be the biggest displacement, and then we have a variation of displacement going down to 0 down here. But what about these displacements? Well, these displacements are displacements that the equations computed, because we run a in order to assess, to simulate and to reproduce the initial stress conditions. But these are not displacements due to the excavation of the tunnel, due to the diaphragm wall. These are just computational displacements that we computed to get to the initial state of stress. So when we will go ahead and start a new stage for the construction of the tunnel, the diaphragm or whatever, we have to get rid of these displacements. Otherwise, we'll get confused, because we will see a displacement going down the tunnel. So we have to get rid of this, and this is what this guy tells us: displacements need to be zeroed before starting other stages. So keep this in mind. If we use method 1, and in order to assess the initial state of stress, then that means we have run one computation cycle. We have computed displacement, stresses, and strains as secondary quantities. So we keep stresses and we keep the stresses because that is what we wanted to get, but we delete the displacement. We zero the displacement. We tell the model, oh, just forget the displacement, start again from 0. Hold the state of stress, but delete the displacement. Okay? So we have to remember this, otherwise this may cause errors in the other stages. Okay, now any comment? We can relax a second before we proceed. Any comment, any query? No one? Okay. So next step is that of defining the stages. That is, we call it step number 5. We are almost at the end. Step number 5. How do we define stages? Well, we already defined one stage. If we want to use method 1 to assess the initial state of stress, we said we need one fake stage to get to the initial state of stress. So that is already one stage, if you want. But if we are in a situation like this, we can assess, we can input directly the state of stress because we have estimated it in a simple way, then we don't need that stage. And we can start from stage 0 and go on with the construction stages. Now, with the stages, we are able really to follow the construction. So here, engineering really comes into it. Civil engineering really comes into it. Because we have to know what we're modeling. We have to have a clear idea of the construction stages. And for example, in this situation, we said one excavation, installation of the primary line, second excavation, installation of the final line. These are 4 different stages. But in fact, we can go even deeper than that. Because when we excavate, number one, when we excavate the first cross section, you remember from rock mechanics that we, in order to simulate an excavation, we decrease the internal pressure, isn't it? And we can do that gradually. If we do it gradually, it's better than doing it at once. So that means we may run separate construction stages to simulate the excavation. Because you may remember in rock mechanics that when you put the primary lining, you need to define the amount of load that that primary line is going to support. And you do that by looking at the characteristic line of the tunnel. Do you remember that? And the characteristic line of the support, and you find an equilibrium. So this is exactly what we have to do now here. And in order to simulate that, it means playing with the internal pressure inside the tunnel. Because when we do step number one, excavation, we can put an internal pressure, and then we can remove it to make a full excavation. But when we remove it, we can put the primary lining, for example. And in that case, the primary lining is going to get P0 minus Pi, and so on. So we'll go into it. I went through it quickly, but now we're going to do it slowly. Okay, I see some faces. Maybe those that haven't gone through rock mechanics are a bit disoriented. But we'll go into it. So what we have to do now is to follow closely the sequence of the construction of a tunnel in this case, but it could be a diaphragm wall, of a foundation, of whatever, any geotechnical problem we want to study. We have to follow closely the construction sequence, which means knowing also the construction sequence. You have to know that. If you are the modeler, you have to know the design very well. But look, there's another thing I want to mention here. We can run the analysis with this construction sequence. Then we look at the results and we say, I don't like it. There's too big convergence. We can go back here, change the construction sequence, and run the analysis again and see if the convergence is now better. It's not. We go back, we say, let's make this thicker, and we try it again with the model. By trial and error, we are designing, isn't it? So this is a very helpful tool for a designer, because you can test a number of construction stages, a number of structural elements, of dimensions, of properties, without needing to do it by real, but just on a computer. And then you can choose the best option, and you go and you make your verifications, you see if everything is working, and your design is done. So that's why this is a very, very powerful tool, because you can test a number of things that you could not do in reality, or you could do in reality, but with a cost which is enormous with respect to this. So let's see, for example, let's go into the detail of it. Let's see, for example, the simulation of an excavation. Look, this is the ground surface. This is what we want to excavate. Okay, so we are making an excavation, maybe because we want to create this kind of area to design a highway or a high-speed train line here. That's it. So we want to excavate this. What we say here could be said for the excavation of the tunnel. It's the same. Just the geometry is different. So we call this area A, the area we want to excavate, and the rest of the model is area B. So set the initial state of stress and specify the elements to be excavated in the A area. So we have the initial state of stress, and we say that we want to excavate this. If we want to say the same for this model, it would mean set the initial state of stress and say we want to excavate elements inside here, which we don't have now, but let me draw the element. Sorry, mesh is really horrible. Do it again. Okay, so we have the mesh inside there, and we want to say, okay, this is the area we want to excavate. In fact, if you want to simulate this construction process, it should be only the upper part. 1, 2, okay? I'm going to change the drawing, but you have this too. Determine the equivalent nodal forces, T, to be applied to the excavation boundary to simulate removal of the elements. No displacements or changes in stress occur if material is removed, but replaced by tractions, which are equal to the internal stresses in the soil mass that acts on the excavated surface before A is removed. So this is easier to be seen in this picture than in that. Look, along these boundaries, we have some forces applied to the nodes that we have on these boundaries. Why do we have forces? Well, because the material in area A has its own weight, so it's pushing on that boundary, so it's applying some forces. We have to compute those forces. The exam here is applying some forces to the elements here. You have to compute the forces we have here. And we can do it up here. And those forces, we call them T, just to make it general. They would be, in this case, they would be forces like this, and then like this, and then like this. In the tunnel case, they will be, I don't have it, right? They will be forces this. Okay? We compute those forces. Once we compute those forces, look at what we do. We apply the traction minus T at the excavation boundary when material is removed by deactivating the elements in zone A. So what we do, we have the forces here. We apply a minus T. So in the case of the picture there, the forces are going up. Here they're going down if you want. And by applying the inverse of that force, we simulate the excavation. So in practice, in your numerical model, you will go here and say excavate, and you will see the graphics that you are removing the elements. You will see this on Thursday. You simply click there, and the elements will disappear, like if you are excavating. But in fact, they are not disappearing, because the model still have each node, each number of elements, they're still in the model. So they're still there, in fact. You see them disappearing, but they're not disappearing, they're still there. So how do we consider excavation? Well, we do not physically remove the elements from the model, but we apply forces at these nodes so that we simulate the excavation. This is what will happen in the numerical software. Okay? You will see that when you do it in practice with RS2, the software we're going to use, it's like excavate and you will see the elements disappear, which is very very easy to understand. However, what's going to happen is exactly this. This is applying forces on this boundary. We compute those forces. We put minus to those forces. And that is like simulating the excavation. So that's why we say here, no displacements or change in stress occur if material is removed, but replace it by forces which are equal to the internal stress in the soil. Okay? And this is how we simulate excavation stages in a numerical model. I'm not sure you can see well this picture, but you should be able to see some forces somewhere here. But there is a better picture. Yeah, this is probably better. Okay. So look, this is a tunnel, very similar to the one we have here on the blackboard. So we have the crown, the invert arch. This red part is just it's a consolidated area around the tunnel. Okay. So this is the excavation. So probably in this situation here, we had a pre-consolidation of the area, then we did the excavation under this consolidated arch. And the green arrows that you see here are the computation of the nodal forces. So these are the nodal forces. Now, in order to keep the tunnel stable, we have to apply these nodal forces in the other direction. Can you see them here? So we simply change the direction. So we compute them and we apply them like this. If you apply them to the same quantity, nothing is going to happen because it's action and reaction. Okay? Nothing is going to happen. But if we take the black arrows and we apply what is written there, a specific degree of relaxation, which means instead of applying the full force, I say, let's put 80% of that. What does that mean? That we are excavating 20%. And if you apply 20% of the forces, we are excavating the 80% of it. If we apply 0, we have a full excavation. So for those that went through rock mechanics, this is lambda. Remember that lambda? There was 0, 2, 0, 4, 0, 8, 1. That's it. So if you apply a degree of relaxation, then we can simulate the excavation. If those black arrows are taken as 0, then we are simulating the full excavation. But if we do it gradually, for example, stage 1, just 50% of the black arrows. Stage 2, 0. Then it means we simulate the excavation in 2 separate stages. The first one with half of the excavation and then full excavation later. So we can, by using this, we can simulate a gradual excavation. And we say relaxation. We use this terminology to say relaxation because the excavation takes place slowly. This is done for a tunnel, but we could say the same for this. We could apply it at once, so we have full excavation, or we could do it 50%, 60%, and so on. Okay, what we say for the tunnel also pertains to any kind of excavation, like the excavation of for the diaphragm wall, and that's it. So any query here? What are we seeing here? What is this? How do you call this? Rock mechanics people or tunneling course. This is the characteristic line. Great. So for those who have never seen this, I suggest you go and have a look to some notes, some books. Chapter 8, I think, of the book, my book I mentioned to you. They describe this. Look, this is it's called the characteristic line. Here we have the radial displacement, and on the vertical axis we have the pressure or the stress, and we say gradual distressing at the tunnel boundary, which means that before the excavation we are up here, no displacement and initial state of stress. Okay, so for those that have not done rock mechanics, this point shows you the initial state of stress. This one, P naught equal to 1, so this is equal to this one, and we usually call it P naught. P naught. So this one is P naught, and there is no displacement. When we start to excavate, what happens? We reduce P naught. Let's go back here. We reduce the black arrow from P naught to 0. In this case, here you see that the arrows are all different because the elements are all different. So when we say P naught to 0, it's a bit simplified. Reality is a bit more complicated, but the concept is the same. So we go from P naught down to 0, and depending on the properties of the ground, you will follow one of these lines. We don't need to go into this detail, but you remember that this was the elastic behavior, then you have the elastoplastic behavior, and this was at full excavation, the radial displacement you got around the tunnel. So all the points in the middle can be different stages of the excavation from initial state down to full excavation. And when you use this to design, you were putting here the characteristic line of the support and finding an equilibrium point and saying, okay, this is the displacement I will have, and this is the load I will have on the line. Do you remember this? Okay. So in this case, we can do the same, but it's going to be the software computing it. We will need to simulate the excavation. We will need to tell the software at which stage do we put our lining, and then the stresses on the lining is going to be the result of the computation. You've probably seen this picture already. It's here just for a refresh and to show it to people that are not that familiar with it. So if the tunnel has been excavated in this direction, so this is the face, the excavation phase, this is the tunnel we are excavating in this direction. This is what we usually have as, let's say, the radial displacement around the tunnel. It's 0 if we are here, a lot ahead the excavation. Of course, there's no excavation, why should we have a displacement? It's the total displacement when we are down here, because the tunnel is fully excavated. So basically, it's 0 when we are here, it's the total displacement when we are down here. 0 total displacement. So this is the beginning of the characteristic line, this is the end of the characteristic line, and all the rest is in between. And this is a 3D situation because the phase, the excavation phase is advancing, and we call this a 3D effect of the advancing phase, but we usually model the problem in 2D. We're doing a 2D model here also, so we need a trick to go from 3D to 2D, and the trick we use is that of the lambda, or the internal pressure. And we say, well, when we are down here, lambda is 0, that means the internal pressure is equal to P0, to the initial state of stress. Nothing is happening. The black arrow, this black arrow, these ones are exactly the same as the ones we have computed. Nothing is happening, not at all. There's no excavation taking place here. When we get closer, lambda is between 0 and 1, and P, internal pressure is reducing, is less than P0, but it's not 0 yet, it's in between. And when we are far away down here, then lambda is 1 and Pi, the internal pressure, is 0. The excavation is completed. So we can study, by assuming an internal pressure or a relaxation of our forces, we can study different situations. And why do we need that? In order to simulate construction process and the proper installation of preliminary or secondary lining. Look at this picture. It's similar to the previous one. It tells you the same thing, but I added the line so that we can talk about the line. Look, consider that this is, let's say, the reference cross-section for our numerical analysis. So before the excavation is built, this is an undisturbed rock mass. So Pi is equal to P0. We are in the initial stress state, the first stage where we compute the initial stress state. Then the excavation comes here. It's just, for example, the face is at the at our cross section. So that means that Pi is less than P0. We can apply a value of relaxation. That would be a parameter we will need to set as engineers. How much relaxation? So we will need to use the curve of the previous slide to assess that, maybe the characteristic line, and we can assess this. Then we go further, and this brownish stuff is the concrete lining. Let's assume we apply the concrete lining here. So if we go ahead, we will have an additional decrease of the internal pressure. And then when this is very far away, this is going to go to 0. So my query is, what is the load that is going to go on the concrete lining? Will the concrete lining get P0, the initial state of stress, the full load, or will the concrete lining get less than that? You can answer from home also. Looking at this picture, what do we expect go on the concrete lining? The full P naught or just a portion of it?
I was not on this question. That's why I wanted to you said here it's review on 1 month, 1 day. So maybe I say like if it goes at the end it's 0, so it should be 0.
Should be P0, while Erika says just a portion. So let's focus on Erika's statement. Just a portion of it. Look, a portion of the internal pressure was dissipated here due to the excavation. Now we have P naught less than Pi less than P naught. A portion was this, let's say that this is 70%, for example. So we had a portion of it dissipated. Then we installed the lining and we reduced to 0. So the lining is only going to get the portion we have here from now on, not what happened earlier. But this is correct, because when we excavate the tunnel, we first excavate, so we have some relaxation, some convergence. Then later, and depending on the construction sequence, we go there, we install the lining. So the lining is not going to get the full load due to the excavation, but only a portion of it, as Erika said. Then, what is that portion? How much? Well, this is an issue. This is an issue because choosing the appropriate relaxation factor is not always that easy. Those of you that went through rock mechanics saw these kind of curves. They also saw how to compute this line. I'm sure you remember the Panay equation, don't you? You did rock mechanics for sure. So do you remember Panay equation to get that? So maybe go and have a look to that. There was one from Carranza Torres also. One was for elastic material, the other one for elastoplastic material. You probably said, oh, this is 0. You probably saw this picture, 0.28. The total, this is for an elastic material. We assume it's almost 1/3 of it. So 1/3 of it means that before we can do anything, we already have 1/3 of displacement gone. So for sure, the lining is not going to take 100%. Erika is right. It's just a portion of it. And often it's less than 50%. Because for an elastic material, it's 30%, but no one is going to put the lining exactly during excavation. We will always put it a little bit later. When you need to do it very fast, it would be 1 meter from the face. That's probably the best you can do with a steel set. You go there 1 meter beyond so it's not going to be here. It's going to be 1 meter back, which is even more than 0.28. And with Carranza Torres for an elastoplastic material, this is going to be almost 0. It depends on the parameters, of course, but it's going to be in the range of 0.5 and so on. So this is it's an issue in our modeling. It's a complicated part of the modeling that we have to look after, and we need to define these values. Let me show you an example that maybe can clarify this. Then we can go back if you want. So look, here we have a problem where we have 2 twin tunnels which are excavated below ground surface, close to the ground surface. This is the ground surface, and you also have here a highway. This is these are 2 twin tunnels for the high-speed railway lines between Torino and Venice. It's a section between Milano and Venice, in fact, and they go below a highway. Okay, so we want to model the problem and see if we have problems with the highway and design mainly the lining of these tunnels. Okay, so stage number 1, gravity turned on. This is the first step. This is a shallow tunnel. We cannot do what we did here. We need to compute the state of stress by setting the unit weight and applying gravity. So that's step number 1. And then what do? We delete the displacement after that stage. You remember that. So step number 1, gravity turned on. Step number 2, distributed loading on the surface. Just to simulate that there is a highway here, there are trucks and cars going, so there is a bit of distributed load. Displacement are zeroed at the end of the calculation. So in this specific case, we deleted displacement after stage 2 because also the displacements due to the traffic load needs to be deleted. Okay, not only that of the gravity, because also the traffic load, we can consider that as a pre-existing load. So it's something that happens before we go there to excavate the tunnel. So that's why we delete the displacement. We only use that to assess the initial state of stress. Step number 3, stage number 3, excavation with 80% of relaxation. So in this case, the tunnels you see, they are circular. They are excavated with a tunnel boring machine. So we excavate the tunnel and then we place the lining, and it's directly the final lining. We don't have primary and finally. It's directly the final lining. I don't know how familiar you are with the tunnel boring machine. Later on, I will give you some information on that, on a little bit more details on how we do that construction process. Anyhow, we excavate full face and we install the lining at the end of the tibia, which, at the end of the head of the tibia, which usually is at 1 diameter from the head, from the face. Okay, more or less, that is how it is. Maybe a little bit less than that. So in this case, we assume 80% of relaxation. So here you can see the red forces which are applied there. They are not the total forces, put with a minus, but they represent 20% of it, because we want 80% of relaxation. So we have computed the forces, and we only applied 20%. All the rest is gone with the excavation. Stage 4, finish the excavation, so 100% of relaxation. I don't see if there is a line there. Yeah, there is, sorry. I don't see it very well, but this is 100% relaxation with the lining placed on site, which means that on the lining, we will have 20% of the load, basically. Because we had 80% before that, then we install the lining and we go to 0, and so the lining is going to carry 20% of the load due to the excavation. Look at some results. This is results at stage 3, and this is the results at stage 4 in terms of displacements. So we will be used to look at charts like this, very nice, colorful plot. You can see how the displacements are distributing. These are the total displacements around the tunnel. You can see here that the maximum displacement are here at the invert arch. That they are located. Of course, this depends on the stress state, on K0, on material properties. And with these red area here that you see around the tunnel, we are seeing the plastic zones around the tunnel. And this is obviously influenced by stages that we have selected. So 80%, 20%, that was a big decision we had to take when we did this design. It's deciding the relaxation. Right. So how is it? Did you get the point, more or less? From home, any query? So let me go back on the same topic, but let's see it in a, maybe just to summarize, okay? So I would say that all our problems will involve construction or excavations, okay? Also, for example, in embankment, problem number 1. This is a construction situation. Instead of removing, we are adding. And so also construction is to be done in a similar way, because simulation of this is done by activating elements instead of deactivating. So here we said, okay, we remove the elements, but we said it's just fake removal because we are computing the force of the elements still there, and we say we deactivate them by applying those forces. If you want to simulate the constructions, we have to do the other way around. So at the beginning, we deactivate the elements when we start, but then we reactivate them later. So we add the forces later. This is what we do in that situation. So it's a contrary. When we excavate, we deactivate. When we construct, when we build, we reactivate. And this also occurs here. Because when we excavate, then we put the final lining, it means we have to activate again the elements, because there will be a lining there. So this is what we do. But let's look at it in terms of a construction of an embankment, okay? So all elements in the embankment are deactivated up to the stage when the embankment is to be constructed. Gravitational equilibrium is attained for elements representing the ground. What does this mean? We want to simulate this problem, okay? So we build the geometry. The external boundary of our model is this, and watch out, goes up there, and then comes down. That's the model, because later we will want to simulate the embankment. So when we build the geometry, when we discretize, we already need to know where we want to go. So all this is the model. But then when we set boundary conditions, this is a surface layer, so we will put rollers. This is going to be a free surface. And at the stage number 1, we are going to deactivate these. We don't want to have them at the beginning because we want to simulate the construction. So we have them in the model, but we deactivate them immediately. So when we plan the geometry, we have to consider the elements already, but then we deactivate them immediately. So for example, here we say gravitational equilibrium is attained for the elements representing the ground. So we only apply material properties to these elements here. We run a computation cycle, we compute the initial state of stress due to this model, and that's the first stage. The incremental displacement computed are 0, as usual. Okay, this was just to compute the initial state of stress, we zero the displacement. Then what do? We want to simulate the construction of the embankment. So let's do it with 3 layers, for example. So in increment 1, layer 1 is to be constructed. So we build the first layer. So all the elements in this layer are activated again. So they're made active. Now they're part of the mesh again. Well, they were there anyhow, but now they're active again. How do we activate them? We assign material properties and a constitutive model to those elements there, which means also a unit weight. So those elements, now on, will carry some load on the surrounding layers. So if we make another stage of computation, now that is going to apply a load to this part of the element, and we can compute the effect of the construction of the embankment. And we can go on like that. So then in the next stage, we will activate the second layer. In the third stage, in the fourth stage, we can activate the third layer, and we can simulate the construction of the embankment. Okay? So construction and excavation is a matter of activating or deactivating elements. And we can play with that to do everything. In a problem like that, we need to deactivate them at the beginning and then reactivate them later on. In a problem like this, we have them at the beginning and deactivate them. Then we reactivate them again when we want to simulate the final lining. So we go back and forth. As I said before, elements are always there. But we don't see them every now and then, depending on what we want to do. We deactivate them. We don't take their, we don't consider the presence, their effect, depending on the stage we want to do. Okay, so we're going to go through these procedures of excavation and constructions many times, because we will have to deal with that. in all our geotechnical problems. So we will see different examples of this. Just to close the lecture, I want to mention the last two steps, and then we'll see the examples next Thursday. Last two steps are computation and interpretation of our model. So at this stage, we need to compute the model. This is the window you will see with the software we're going to use. When you compute, you see the blue arrow is showing you how you proceed, and you have a number of things here. What do you read here? Can you read? No, you cannot read. This is written iteration, and this is the maximum number of iterations. So you can't validate computation. Particular example in 500 here. So this is the 500. In screenshot, we are see that until we get to below the top and you understand. And also we're back to this later on, of course. Yes, I do one more. So next is that of the interpretation. So we need to look at the data we got and check if things are properly done, if they match expectation. We lost the video, so something is going wrong here. So that's closed because it's time to finish, but I don't see Professor Foddy yet. Oh, here it is. Okay, so we can stop. So we will start again on Thursday. We will close in with computation and interpretation. We will say much more about the interpretation stage next Thursday, okay? So see you on Thursday online. Remember that on Thursday we have 4 hours and a half in a row. We have a short break after the lecture, but then we have to go for the group project. Okay, also from home, see you. Bye-bye. Stay safe.